This video, we cover our content for the second part of the extreme value theory, part of the unit, that is the threshold exceedance method and the generalized Pareto distribution. Again, you can find those slides on the web from any browser, but they're also there's a link to them on the Ed discussion forum. So first thing we do is illustrate the Picklands-Balkema-de Haan Theorem by generating random observations from different distribution, taking the exceedances of this data above a certain high threshold, and see what the shape of the distribution for this exceedance data is. So we do that as usual in our custom function declared here, and as the sample size, U is the threshold above which we take the exceedances. This would be the random generator you have, the parameters of this distribution. So here it's assumed it's a two parameter distribution. Okay, and then the seed for our simulations. Again, if you always set seed to 1 in this command, you're going to replicate the same exact simulations. If you change the seed, then you're going to get a slightly different result because you're going to have different simulations. Okay, sample is simply our initial sample before we do anything to it, meaning before we take the exceedances, okay, of size n with those two parameters. Now this is where we take the exceedances. So to be consistent with the notation in the slides, I call W the exceedance above a certain threshold. So what R is doing here, I take my sample, and here in between brackets, I only keep all the data points that exceed U. And this works in R because this command generates a vector of true or false. So for every point, for every value inside sample is going to be true if that specific point is above U, and in which case sample true is going to keep that point. And if sample or the data point here is smaller than U, then it's going to have a false, and then the operation sample bracket false is not going to keep the data point. I encourage you to try this in R to make sure you agree this works. It does what we want. Keep only the points that are above U, and then careful that we keep the exceedances above U, meaning we subtract U. This gives us what we want, our sample of exceedances. And then simply here, as we've done before, we plot a histogram of this of those data points to see the general shape. Here, I just want to see overall what's the shape of exceedances for a few different distributions. So let's try. First, for here a uniform. So I just use a uniform. In R, if I don't specify any arguments, it's going to use the default arguments, and the default arguments of R unif are 0, 1, meaning we simulate from a uniform with bounds 0, 1. Now, we've done the theoretical work, and we know that the uniform is in the maximum domain of attraction of the GV with C equals to -1. But this, via the Picklands-Balkema-de Haan Theorem, means that the exceedances are approximately generalized Pareto with a specific C of -1. Now here, in fact, you might note that exceedances for a uniform are exactly uniform. They are exactly uniform. Well, yes, it's a simple calculation. If you take a uniform and, in fact, you truncate it at whatever value, the random variable for what's above that value is uniform again. You can do that. It's a simple calculation. Okay, so here, in fact, we don't need the big guns of the Picklands-Balkema-de Haan Theorem, because we have the exceedances for whatever threshold. Doesn't need to be high. Exceedances are exactly uniform. And of course, this is what we observe. If I take a threshold that's not especially high, because for a uniform 0, 1, 1 off is just the mean of the uniform, we have that roughly it looks the exceedances uniform. If I take a different threshold 0.9, again we have that it's uniform. So here the theorem is not well, it works, of course, but it's not especially useful because we already know exceedances are exactly uniform. Now, if we take a case of a different distribution, the normal. Now we've presented in the slides that the normal, well, I think we've said it without proof, but it's in the maximum domain of attraction of the GEV with C equals 0, which again via the other important theorem, the Picklands theorem, We also know that exceedances should then be should then have approximately a GPD distribution, but also with Xi equals 0. And this corresponds to a uniform distribution. Like if you go back to the slides, a GPD with Xi equals 0 is in fact a uniform, what did I say? An exponential distribution, sorry, an exponential distribution. Okay, and so let's try. We generate data from a normal. We take a threshold that's not especially high, okay, because 1 for standard normal is not an especially high threshold. Okay, data, maybe it looks a bit like the shape of an exponential. If we increase the threshold, then it looks even more like an exponential. Here, sorry, I didn't put the theoretical true line. Maybe I should have, but it's just to give us a feeling of what we said, that for distribution that are in the maximum domain of attraction of the gumball, okay, of the GEV with X equals 0, we also expect the exceedance data to follow roughly an exponential distribution, because the exponential is the special case of the GPD with Xi equals 0. Okay, but now we try again with a heavy tail distribution. So if the initial distribution is, here we use as an example the student, but a student distribution with especially for small degrees of freedom, here 3, is a heavy tail distribution, meaning it can have values that are pretty big with some relatively high probability. So let's try. We generate the data as a student. It's in the maximum domain of attraction of the GV with a positive Xi, meaning the exceedances should be roughly GPD with a positive Xi and GPD with a positive Xi as a Pareto, so it's a heavy tail distribution. Okay, and again, this is more qualitative. This is what we see, because if we take, again, here, let's start with the threshold that's moderately high at 1. Okay, yes, the data looks substantially heavy tail, because although the bulk of the data is here around from 0 to whatever, 0 to 2 or something, you do have observations that's far away from that. And if we increase the threshold, we see that probably even a bit more substantial, that the data, but it's actually similar trend. Okay, but the data does seem to be more heavy tail than in the exponential case. Okay, but again, this is more qualitative to illustrate a little bit this idea that exceedances have their own distribution, and asymptotically, it is the GPD with either negative, 0, or positive Xi. Again, depending on which distribution you start with, the overall trend is that if you start with a distribution that's light tail, you will get exceedances that are light tail, meaning with a negative Xi. If you start with distributions that are kind of medium tailed, light tail or medium tailed, you're going to get a Xi of 0, meaning the exceedances are exponential. And if you start with a distribution that's heavy tailed, then you're going to end up for a distribution of the exceedances, which is heavy tailed. But now maybe the main topic is fitting data to the GPD. So we want to apply the method we've seen in the theory part of the slides. Maybe let me share just 1 second. In this section in the slides, model fitting, we explain how to do this theoretically. Now we illustrate it in R. Now the sensitive step is to choose an appropriate high threshold U. We will do that in a function, and we call this function fit GPD. And one of the arguments of the function will be this threshold U. So you can do it again by just recalling the function with a different U and see how the results change. And here, okay, this is the code. Let me review it. And this is my code. I'm sure there's other ways you can do something equivalent. But here, the way I've done it is I need to, at least the way I do it is I separate the cases where the density is for non-negative Xi. Now here, not to bother with notation, I'm going to, what I call S is sigma, and what I call little e is Xi, okay? I guess because I didn't want to have those equations to be too long. But again, S is sigma and E is Xi. So I'm dealing with the case where we have a non-negative Xi. So Xi could be 0 or positive, and then I deal with the case separately. I declare a separate density. I'm going to call it GPD2 or DGPD2 for the case where Xi is strictly negative. Why do I do that? Well, it's because they have different support. In the case where C is non-negative, I can deal, so because it's a distribution for exceedances, the support is always starts at 0, right? It needs to be positive. Okay, so if X, the argument here, the first argument is negative, then it should be, the density should be 0. But then in the case where C is non-negative, it doesn't have an upper bound. Okay, the distribution, the GPD doesn't have an upper bound. So then I can just declare this and I'm done. But for the case where C is negative, it has an upper bound. So then I need to deal with this case in the density. So if X is negative, then again the density should be 0, because it's impossible for an exceedance to be negative. But then there's also an upper bound, and if you look at the notes, the lecture slides, you see that the upper bound is this thing. Okay, this thing makes sense. Remember, C is negative here, so minus S over C would be a positive, and the upper bound. So it's impossible under this theoretical distribution for X to be bigger than this upper bound. So then if X is bigger than the upper bound, the density should be 0, and then you have the expressions for the density. And here you have a nested if else, right? First one is, okay, if X is 0, return 0. Then we go here, and then if X is positive, if X is positive but bigger than this, return 0. And then if none of that is true, return this. Okay. And by the way, I didn't say, but here, as we explained in the theory, we only need to implement the 2-parameter GPD, because the theorem tells us that exceedances, they have a mu, the first parameter is just called mu of 0, so we can only fit a 2-parameter GPD to our exceedance data. Okay, and now of course we do this with maximum likelihood, but then here there's a bit of, the code is slightly more complicated because we need to deal with this case and this case. Okay, but I do this in the function I call fit GPD. The arguments of the function are my initial data. So this is the whole sample, not only the exceedances. But then my code is going to pick only the exceedances above U. So U would be an argument of my function. And then I tell one of the arguments is negative E equals false. So if negative E is false, it means I want to use this density. And if this argument negative E is true, then I want to use the second density, which is for the case where C is negative. Okay, first step is simply to define my exceedance data. So same trick as before. See, my data is the sample I fed to my function, and again I do the same trick. So I keep only the data that's above U. And notice how I make an effort to say data, right, the Australian way, but sometimes data might come back. But anyway, those are my exceedances above a certain U that I've chosen here. Okay, negative likelihood, and this is what we want to minimize, because of course we want to maximize the log likelihood. So we want to minimize the negative of the log likelihood of our data. Okay, we deal with the two cases. If we have a negative E or negative C, so if this is true, then we will use in our negative, the log likelihood, the function density GPD 2, which was for the negative C case. Okay, and this is as we've done before. Negative, the likelihood is just a negative of the sum of the log of the density evaluated at every data point. Okay, for our two arguments, or our two parameters, P bracket 1, P bracket 2. P here being a vector. Okay, and then else, if we're not in the negative case for C, then we do exactly the same thing, but we use the GPD 1. Yeah, and then what happens? Okay, we can find here in this case, it's relatively easy to find the method of moments estimates of the two parameters. Okay, so I'm not doing it, but maybe maybe you can try to do it for yourself, or maybe I'll give you in the tutorial exercise to find the method of moments estimate of C and the method of moment estimate of sigma. Okay, and then we do the optimization, but here there's a additional complexity, because in the same function I'm dealing with both cases. I'm using a constrained optimization, meaning I'm gonna tell R, okay, optimize this function, in this case minimize the negative, the log likelihood, but under some constraints I do not want C to be positive, okay, if if I've called this argument negative E is true, right? Because yeah, that's why I am telling R I am forcing it. I'm forcing the Xi to be negative or positive. Okay, so because of that, I need to use a different function than the one we've used before. I'm going to use this function in R called the const optim for constraint optimization. But it's not overly complicated. Let me explain. So again, I have two cases to deal with. Yeah, so this is used in the optimization to force C to be either either bigger than 0 or maybe here I should have said smaller than 0, but there's two cases. So here I declare a matrix that's going to be used in the constraint. Okay, and that matrix seems a bit okay, it's a bit not clear what is this what this is, but it's simple. Let me show you in a second on a different document. Well, actually, let me show you straight away. I'll just share a different screen. So this is a matrix that is used in this constraint optimization function. I'm feeding this. So math is just an arbitrary name I've given, but I'm feeding this to the argument that in this function is called UI. And you see there's another argument that we need to use, which is CI, and this I give it 0, 0. Now, this is the matrix I'm feeding to UI, and CI I'm feeding it 0, 0. Why does that make sense? How does this give me a constraint optimization solution? Let me show you in a document here. Okay, so, and by the way, you can of course type in the R console, question mark const optim, and then you're going to get some information about this function. But in essence, what this is doing is it's taking this UI. Okay, and let's do the negative case first. So for the negative case, this is the matrix I'm feeding to the argument UI. Okay, this is the matrix I've called in my code MAT. Okay, MAT. What the constraints is doing is it's taking the UI matrix and then it's multiplying. This is the symbol in R for matrix multiplication. Okay, because if you only add the star symbol, this would be a element by element multiplication, but that's not what we want. We want matrix multiplication. So it's taking this matrix and it's multiplying it by, this is arbitrary name I given, just P. I just mean the two parameters we have. Okay, we have a function of two parameters we're optimizing. Okay, so for us, what I call here P arbitrarily is sigma and Xi. Okay, so it's taking this matrix times the vector of parameters minus the CI. And remember, for us, the CI was 0, 0. That's what I put in my code. Okay, and the way it works is that this is an equation that R is going to optimize. But you see, there's the equation is this vector, because here you have a 2 by 2 matrix times a 2 by 1 vector minus a 2 by 1 vector. This yields, of course, a 2 by 1 vector. Column vector needs to be bigger than 0, 0. But you see, I've chosen this matrix to give me what I want, in the sense that if you take this matrix multiplication, okay, this matrix times this vector, you get obviously just 1 times sigma plus 0, so you get sigma here for the element 1, 1, and then on the bottom you get minus Xi for the element here of this vector 2, 1. Okay, but then the constraint is that this thing, okay, then minus 0, 0, that doesn't do anything, needs to be bigger than the column vector 0, 0, meaning sigma needs to be bigger than 0, or bigger or equal, and then minus Xi needs to be bigger than or equal to 0. But this is exactly what I want. I want sigma to be bigger than 0, and I want minus Xi to be bigger than 0 because I want Xi to be smaller than 0. Okay, now here you might say we have a bigger or equal. That's not exactly what we want. We would like a strictly bigger, because we don't want sigma to be exactly 0, and we don't want Xi to be exactly 0. That's true, but I don't think it's going to matter in practice. But if you're bothered by this, instead of adding 0, 0 here, you could put 0.0001, such that sigma bigger or equal to 0.001. It's kind of saying sigma needs to be bigger than 0, if you see what I mean. Okay, and that's it. Let's just do the case for a non-negative Xi. I would feed to my, as constraints for my optimization problem, I would feed the function simply the only difference here is the minus 1 becomes a 1. Well, yes, because then this gives me sigma bigger than 0 and Xi bigger than 0 as well, and this would be the case where I'm forcing the function to return a non-negative Xi. Okay, so this is simply explaining the syntax of this R function. Okay, so let me go back to the code. Okay, and then so this is what I'm doing here. I'm feeding the constraints matrix, and then here it's kind of arbitrary, but I'm because I've tried this before, and if I don't, when I'm in the non-negative E, I'm gonna start the optimization at arbitrarily small but negative value for Xi, and same thing. If I'm in the case where I want a non-negative Xi, then I'm going to feed as initial value for the optimization. I'm going to feed a slightly positive number. And then I believe that that's it. You know, because you might wonder, why don't we just feed the method of moments estimate? Well, nothing guarantees that, you know, this, I suppose, might be negative when I'm in the positive one. So in the positive case. So this is why I'm going to force I'm going to force this to be either positive or negative based on what I want. Okay, and then we do the fit const optim. I'm feeding the method of moments estimator for sigma, and then I'm feeding the EI, which is the you know, either the small negative one or the small positive one. What I'm optimizing is the negative, the log likelihood. Again, this UI is my matrix of constraint. This CI is the 0, 0. Grad equals null. Don't worry about that. There's a way you could feed the gradient of the function, like kind of manually to the function, but here I'm not going to bother with this. Maybe it would be better to do it actually, but it seems to be working fine with grad equals null. And at the end, I just return the parameters. Okay, hopefully that was relatively clear. And then, so let's move on. So this is my function I've defined. Let's try it now. Okay, let's just try and simulated data. Okay, I need my random generator for the Pareto because it's not implemented in R, but this is exactly the same as we've done in previous videos. So just a random generator for the Pareto. Okay, for my result to be replicable, I'm gonna set the C to 1. Usually I set this to pi. Okay, let's vary things a bit. Set C to 1. Sample size, that's kind of arbitrary to 5,000. Then I generate a bunch of samples from different distributions. Now let's try to fit the GPD to the exceedance data of all those samples. Okay, and here arbitrarily, I'm picking the threshold U to be the percentile 95% of the data set. Okay, percentile in R is as this function quantile of the whatever sample, with this argument being the percentage you want, gives you the percentile, the 95th percentile in this case. And here, well, I expect that for uniform, I should have a negative Xi. So I'm feeding negative Xi equals true. And you see, for the uniform, we expect a Xi of -1 because that is what the theory tells us. And indeed, we're quite close. For the normal, we accept a Xi of 0. And you see on this sample, we get a Xi that's not that close to 0. And here, it's hard to say exactly why. Is it the sample is not big enough? Is it the threshold is not big enough? But maybe you redo this again with a different sample, you might get something much closer to 0. Here, there's random variations, right? So yeah, theory tells us we should be close to 0, kind of close, but not so close. And then same thing for the exponential, theory tells us we should be close to 0. Of course, because as we said many times now, exponential is in the maximum domain of attraction of the Gumbel. So that's a Xi of 0. Okay, we get something close to 0. Same thing, the gamma here. Okay, yeah, I had the gamma with some parameters here. The theory tells us we should be close to 0. We're relatively close to 0. And lastly, for the heavy tail distribution, for the Pareto, yeah, we should have a positive. We should have a positive C. In fact, you can show that for a Pareto with the alpha of 3. Well, we shown. I think did we show that? I forget now, but yeah, we should have the Xi should be I think we showed that it should be the inverse of the alpha parameter. So it should be 1/3. So 1/3 would be the theoretical value. You see, well, we're not super close, but not that far either. And for the T, with 3 degrees of freedom, I'm pretty sure. I think I done those calculations last year, and I'm pretty sure that's why I picked a student of 3 that the theoretical value is also 1/3. Theoretical value is also 1/3. So you see, you're not super far. Okay, so this is just quickly trying our function, but we can do a bit more. We can do the mean excess plot, okay, because this was the tool that we presented in the theory part, that you can plot the mean excess plot, and you expect that past a certain high threshold u, the shape should be linear, either linear decreasing or well, increasing or decreasing. Or if it's flat, then you expect that it means the C should be close to 0. So let's implement this mean excess plot in R. So mean excess plot. This is the E of little u in the lecture slides. So I mean, just maybe I'll show you to refresh your memory in a second. Okay, in this section, we just want to implement this thing. It's called, yeah, mean excess plot. Where's the formula? Okay, it's here. Okay, this empirical, I suppose, version of the mean excess function. Okay, so which is simply taking the average of all the points above u, those points minus mu, and then divide by how many points there are. So it's a simple average. Am I sharing the right thing? I think so. Okay. So this is what I do here. It's a simple function. It takes 2 arguments, a sample and then a threshold. So this is doing what I want. Again, using the fact that in R, so a sample is a vector, and but it's going to evaluate is every single point bigger or smaller than u. And actually here in R, what this is doing is, because this thing, sample bigger than u, is a vector of true or false, true, false, true, false, depending on whether each data point is bigger or smaller than u. But R interprets a true to be equal to 1 and a false to be equal to 0. So when you multiply this vector of true, false times a vector, you see sample minus u is a vector of values, numerical values. It multiplies by, in fact, a series of 1 and zeros, and it's what I want, because if a given point is bigger than u, it's a 1. I want to keep it, and so I want to sum every point here that has a 1 corresponding in this vector. So basically, I'm doing what I want here. I'm summing all the points that are bigger than u, and for the points that are smaller than u, well, I'm summing just zeros. So I'm not summing anything. Okay, and I divide. Same thing. I'm summing. So I take, this is a vector of 0, 1, 0, 1, 0, 1. I'm summing all the ones. Well, I'm summing the zeros as well, but summing zeros doesn't do anything. So I'm finding how many of those points are bigger than u. And again, I encourage you to try this code in R to make sure you agree it does what it's supposed to do. Okay, this is something we've done before. I'm vectorizing the function, meaning that I'm going to be able to pass it a vector of arguments, meaning, well, sorry, yeah, I'm vectorizing, but here I'm saying that it's the argument u that I want vectorized. Okay, so meaning that if I then, after I vectorize the function, if I call EU with one given sample and then u to be a vector, it's going to evaluate this thing for every single value in the vector. U being the vector here. Okay, and then I can use EU to define a new function. Okay, so I call this plot EU. This is again a function that I can call on a sample. And here, okay, so this function plot EU has 2 arguments: the sample, of which I want to plot. Let me show you the result, something like that. Okay, I want to plot for a whole series of threshold. I want to plot the EU of a given sample. But I want to exclude, I want to possibly exclude a few points. We said in the theory that the very last points are extremely variable because you're computing the mean on a very tiny number of observations. So you possibly want to remove them from the plot, and I'm creating a function that has already this option. If NB exclude is 0, then I'm not excluding any points. But if NB equals 1, I'm excluding the very last point from the plot. What do I mean by that? Let me go back to the slides just for a second. You see in the slides, we're plotting the order statistics. So the smallest observation versus EN at the evaluated at x1, meaning it's going to take the average. This will take the average of all the points that are bigger than the first order statistics. But you see, once I get to x, well, xn, e of n of xn, there's no points that are bigger than the biggest one, so this doesn't make any sense. We don't plot this anyway. Like here you see I should be, the biggest I should be n minus 1. But even if we have x n minus 1, maybe we don't want to include this point because we would be computing the average of all the data that is bigger than the n minus 1 order statistic, but there's only one point. Okay, it's x, only x bracket n is bigger than x bracket n minus 1. So we take the average of 1 point. That's not very meaningful. So maybe we want to exclude, you see on the plot, we don't want to see the data point xn minus 1 and en xn minus 1. Maybe we don't want to see the one before last xn minus 2 en of xn minus 2, because again, this is averaging only 2 points. It's not very meaningful. So this is what we're doing here. We possibly exclude a few points in the code. Okay. What I call n here, okay, maybe n was not the best name for this argument. It's simply how many points I want to plot. Okay, so it's not the sample size. Unfortunately, it's how many points I'm going to have on the plot. Okay, so maybe bad Gilly with poor notation here, but I think you'll forgive me. Okay, this is just graphical parameters for our plot. Then what I'm plotting is, again, the order statistics. Okay, so if I sort the sample from 1 to n, well, yes, n, because this is how many I want plotted. You see, if nb equals 0, then I'm going to plot by default sample size minus 1. Okay, because this is what we have on the slides. Okay, you never plot the very last one because there's no points above it to compute a mean from. Okay, but then if I said that nb exclude is 2, 3, or whatever, I exclude a few more, then you see I'm going to plot a few fewer points. Okay, so I'm plotting. On the x-axis, I put the order statistics, and then on the y-axis, of course, is the EU evaluated for the whole sample, evaluated with the U, which is the order statistic. Okay, which order statistic? Well, from the first, the second, to the blah blah blah, to the n, where again n is how many points I want on my graph. Okay, hopefully that's relatively clear. And then those things are just graphical parameters. And we can have a look at some examples. So remember, overall, the trend is this. If the data is light tail, meaning it's in the maximum domain of attraction of the reverse Weibull, it means that Xi is negative. So and you expect this from the theory, you expect this mean excess loss function to be at some point for some after some threshold u to be a linearly decreasing function. Now for the uniform, it turns out that it's linearly decreasing and is very, very almost perfect trend for the whole support. Well, which makes sense because exceedance data is exactly uniform for whatever threshold. Okay, but now for other distribution is going to get slightly more messy, because for the normal, you see it's decreasing, but then it seems to be decreasing at a decreasing rate, and only towards the end. Okay, only for truly large values for the normal do you get that. Okay, it does seem that now it's a flat distribution, which is what you expect for the normal, because remember the normal is in the maximum domain of attraction of the gumball. It's a Xi that is 0, so you expect a flat trend after some high threshold here. And this is, at least qualitatively, what you kind of see towards the end. The trend of this EU becomes kind of flat towards the end. And if we try, okay, if we try to, you see here, this is a bit messy. For the exponential, you also expect a flat trend. The theory tells you that. But there's variability here. By the way, I'm already exceeding the last 2 points. So already the two biggest points, they're excluded. But still, for the last few here, the trend, it seems to be flat everywhere. But then I suppose because the last few points are kind of variable, they don't follow the overall trend. Okay, which is that the theory tells us this should be a flat line. Again, because Xi is 0 for the exponential. Same thing for the gamma. You have increasing, but then decreasing, and the theory tells us eventually this should become a flat trend. It kind of becomes a flat trend, but you see it's a bit messy. Like it's here, it's decreasing, then it's flat, then it's increasing, decreasing, increasing, decreasing. Okay, you might say towards the end, or yes, those points are very variable, but it is kind of flat. Okay, so it kind of matches what you expect, but it's a little bit messy. And again, the rule of thumb here would be that you want to pick a U after which the trend doesn't change, meaning it's either linearly decreasing, linearly increasing, or flat. Here it kind of works. I think if you would pick a U a bit bigger than 2, maybe somewhere here, you might say the trend is there's no trend, it's just a flat line. Here it's flat everywhere, which makes sense because the exponential, the exceedance over an exponential exactly GPD, because they're exactly exponential. Just towards the end, you have a bit of worry because of those points, but I think you can probably exclude them because they're the very last few points. So here, any threshold would be fine, I suppose. Well, I think because it's pretty flat throughout. Here you have a bit, here you have a bit more trouble, but if you pick a threshold maybe high around here, after that, it's hard to discern any upwards or downward trends. It seems to be quite flat. So maybe a U around here would be a reasonable choice. But as I said, you would pick the U and then you would check that the fit is good. Okay, so it's not just, this is just a rough visual guide to help you get started in picking an initial choice for the U. Okay, for the Pareto, that's also slightly messy, which is surprising, maybe a bit surprising, because you know that exceedances for Pareto are exactly Pareto. So you might have expected that the trend would be perfectly linear, but it is linear increasing as you expect, but you see it seems to be breaking up here, and then you have decreasing at a slower pace. It's just a feature of the randomness in the data and the fact that towards the end you take the average of data that's very heavy tail on a few observations, so it's going to be quite variable. If I see this in practice, I would probably say, okay, there seems to be a trend here and then another trend here, so maybe picking a U around here would be reasonable, because it seems to be linearly increasing at a relatively steady rate after a value around here, 9 or 10 roughly. Okay, one last, it was the student, which has an interesting feature, which is decreasing at first, quite it's very almost perfect decreasing trend, and then it starts picking up, increasing, and it's not too bad. Like you see, it's increasing at a relatively steady rate. Maybe in practice, if you want to pick a threshold, you see it's increasing here. There's a bit of a flattening, so maybe you would tend to pick a threshold here, U around this line, because after that it's aside maybe this point, it's pretty the trend is quite good, linear with positive slope. Okay, but I suppose the bottom line here is that in practice, this method is really a rough guide. It's maybe not super obvious what the threshold should be, so you need to do a bit of trial and error. And once you've chosen the threshold, you need to assess if the fit is good, and you can do that with the usual diagnosis tools that we've seen before, comparing the CDFs. Maybe checking if you have a few candidates for what the U should be, you check which one has the best BIC or AIC. You want to run a statistical test like a Kolmogorov-Smirnov to see that your exceedance data is truly a GPD with the fitted parameters. So to make this a bit more concrete, let's do it. Let's do it for a real data example, which is a fairly famous data set. At least I've seen it many times in different textbooks that people use it. Here I need to download this data set. I need to use the library QRM. So you probably need to install it first. So you know how to install a package in R, I imagine. If not, if you have trouble with this, you can let me know on the forum. I also want to find the kurtosis of the data. Well, I could do it myself, but I'm lazy, so I'm going to use this library called Moments that has a skewness and a kurtosis function in it. Okay, and there's a data set here called Danish, and there's one, I suppose one variable that's called fire losses. So for some fire insurance, there's the whole data set of losses. For I suppose some insurance or some insurance company in Denmark, but I have to be honest, I don't know exactly the specifics of this data set, but here we use it for illustration. Now, it's a good data set to apply extreme value theory because it's very heavy-tailed. You see some summary statistics here. The mean of the data is only, I think this is in millions or millions of Danish crowns or krones. What's the money in Denmark? I forget. Okay, 3.38, that's the mean. But then the maximum is 2.63. So you see, and the standard deviation is 8.5. So the maximum is many standard deviations away from the mean, which is a sign of a heavy tail distribution. The kurtosis, which is, some people use it as a measure of tail heaviness. It's kind of debated. Is it a good measure of tail heaviness? I don't have strong opinions about that, I guess, but it's a rough idea that the kurtosis gives you some idea about how tail heavy distribution is. Here it's very big, okay, very big, the kurtosis. And you see the 99th percentile is 26, but you still have data very far away from this. If you do the histogram as the next step, you see it confirms to those summary statistics that most points are close to 0, 1, 2, 3, but then you have some points that are much bigger. Okay, so it goes far away in the right tail. Okay, so that's heavy tailed data. Let's fit to the exceedances the GPD distribution for this data. Okay, here there's another histogram. You see, we take the histogram of the log of the losses just to see a bit better. I mean, then when you take the log of something, it's a bit harder to interpret, but the point here is here we don't see much. Here we see a bit better. And I suppose it's a general trend that if the log of some data is still skewed to the right, it still looks kind of heavy tail, the log of the data, then you have data that's truly heavy tail, because the log, for the log of a point to be 5, you need that point to be pretty big. Log of 250 gives you 5, and yeah, so overall that's just a bit more illustration that this data set is tail heavy, because the log of the data is still asymmetric to the right. Okay, the mean excess plot of losses. Now you see, we do it first without excluding any point, but you see that those last 2 points, they really are far away and not in the general trend. But it's reasonable to exclude them, because again, they're averages based on very few observations. So if we exclude them, then we get something that's honestly very linear trend throughout. So this is a real data set, but it has in a sense a better trend. It conforms better to the theory than data that is truly Pareto, okay, which is interesting. Now, so here, I think it's fair to say many thresholds could be picked and yield a decent fit, but as I think I've said in class, see that around the value 10, something a bit different that happens. It's increasing, then it's decreasing. The pace of increasing decreases. It's almost flat, but then it shoots up again from around 10. Maybe you want to say 12 or something. But and again, it's heavy tail data. You see, the 95th quintile is around 10. So if we pick around 10 as a threshold, we have around 5% of the data that exceed that threshold. So let's try that. Okay, so this is what I said. Around the value 10, there's a sort of kink in the trend, and then a straightening out above this value. It seems reasonable to try with a threshold u equals 10. Okay, so again, the goal is to see if a generalized Pareto is a good choice for exceedance data above 10. Okay, we pick 10 as a threshold. We fit the GPD to this data set losses with a u equal to our threshold that we've chosen here. Again, because we've done that nicely in a function, you can call it again with a different, and you see if the C changes here. So we get the first value, the sigma, I guess doesn't matter too much for interpretation, but the C does matter. See, you get something that's positive and that's close to 1/2. So I think you can say it's significantly positive, fitting the observation here that this data is quite heavy tailed. Yeah, and here I suppose fit GPD, there's this argument is C negative. So by default, this is set to false, I imagine. Yes. Okay. So here, if I haven't specified this argument, meaning I want to fit with the positive C, because this is what I expect will fit better because of the trend of the data, which is qualitatively it's heavy tailed. I mean, of course, you can try again if you want. You can try again with negative C, and then check which fit is better, but I'm almost certain that the positive one is the better choice. Okay. Now we assess if the fit is good. We check for our exceedance data, which again is called W, histogram of W, and we curve the density of a GPD with, of course, the fitted parameters by maximum likelihood, which are declared here in this vector with 2 values. Okay, overall here it seems good. Okay, it seems good. Comparing a histogram to a density is a bit limited. I think it's better to compare the it's better to compare the CDF, but the CDF gives us the similar conclusion that the fit visually looks pretty good. Like the red curve, which is a theoretical one, is very close to the empirical one. But we can do a bit more. We can do a QQ plot. Yeah, I'm going to create my own QQ plot because I guess I'm not sure, but I think maybe because I did that last year and probably don't remember. But if I did that last year, it's probably because the GPD for whatever reason is not implemented in the package I used in the previous video, because I'm usually lazy, and if it's implemented in a different package, I'm not going to declare my own function. But anyway, okay, but this is also has pedagogical value for you, so we can see how we create our own QQ plot. I just need the only thing I need for the QQ plot is to have the theoretical quantile function of the Pareto. Then I can use that to create my QQ plot, and I'll show you in a second. But here, QGPD would be I declare what is the quantile of the generalized Pareto. Okay, I suppose here maybe I should have had a line to explain this, but it's a simple calculation. So you know how to find the quantile function. You just grab the CDF, set it equal to whatever argument, let's call it u, and then you solve for the argument x in that expression. CDF equals u. The CDF has a bunch of x there, the argument of the CDF, set equal to u, and you solve for x. You're going to get x as a function of u, and that's your quantile function, which of course answers the question, what's the value of x that makes the probability to be smaller or equal to that x equal to u, because the inverse of the CDF. Okay, m is just the length of w, how many data points, how many exceedance data we have. Because w, where was w? W is here, my exceedance data. Okay, and then you then create the QQ plot in this manner. What do? We put plot. Okay, yeah, okay. On the x-axis, we put the theoretical values. So we're gonna plot. You see, because I have m points, I'm gonna plot the quantile at okay, 1 over m plus 1, 2 over m plus 1, 3 over m plus 1. I do that here. You might wonder why it's not just m, because in theory, maybe you might say that the first point should be the quantile evaluated at 1 over m because I have m data points, and so the first point it should be it's the empirical quantile 1 over m, because it's the value that makes 1 over m, a proportion 1 over m of the data point smaller than this one. It's true, but I need m plus 1 here, because if I have m here, the last one would be m over m, that's 1, and then GPD of 1, so QGPD of 1 would be infinity, because the GPD with positive C has no upper bound. Okay, so this is just a common trick that you want to avoid the last point to be infinity, so you divide by m plus 1 instead of m. So that's on my x-axis, because it's a theoretical quantile that corresponds to every data point, which is the data quantiles on the x-axis. Okay, which I put here. Sort W would be, of course, the order statistics, W1, W2, W3. So meaning, well, the first point here on the x-axis is the smallest observation. Now, the smallest observation is the empirical quantile at percent. I say quantile, it's the synonymous for percentile. Okay, sorry if I jump from back and forth. Is a 1 over m percentile or quantile. So it says the value such that 1 over m proportion of the data is smaller or equal to this. So the theoretical counterpart to this would be the GPD at 1 over m, but again, I'm taking 1 over m plus 1 because I don't want to have an infinity here. And if m is moderately large, it doesn't make a big difference. Okay. I hope I don't get too bogged down in details, but then what matters here is the interpretation. We add, of course, for comparison, we add the line. It's just a line of equation x equals y or y equals x, because if all those data conform, meaning if the empirical quantiles are close to the empirical to the fitted quantiles, you expect to see the data on a straight line. Here it's pretty good. It's really good. There's a few of the last few points are above the trend, but usually you're not worried about this too much, because well, the data quantiles for very high quantiles, of course, they're very variable, because the last very few observations are the most extreme. So usually you don't worry too much if the last few points are above the trend or below the trend. Okay, one last thing we can do is the goal here is just to assess if our fit is good. If the exceedance data conforms to the GPD distribution, you can do a statistical test. Okay, so you can test, well, I have my exceedance data. You can run the Kolmogorov-Smirnov test with null hypothesis that it comes from a GPD distribution with the parameters that we fitted under the method of moments. The method of likelihood, maximum likelihood. And here, when you run this, you get a p-value that's very big. So it's much bigger than any reasonable threshold you would fit, like you would fix 5% or 1%. So here you don't reject. So it's plausible based on this test that this exceedance data follows a GPD with those parameters, and this it fits what we've seen here, that the fit looks pretty good. Okay, so last comments. Okay, this is what I said. The largest points are larger than expected. Yeah, larger than expected because they sit above the trend line. Meaning this is a data quantile. It's above, so it's above what is predicted, because what is predicted would be the fitted quantile, the value around here. So yeah, it's about what is predicted. But again, we don't worry about those points too much. Now I stop here. Of course, you could repeat the process with different U's, because here I kind of arbitrarily say, look at my plot. Okay, 10 looks reasonable. I pick a U of 10. I do the fit. Looks very good. Maybe you want to try and see if you increase U a little bit, do you get a better AIC, BIC? Could be, though here the fit is quite satisfactory. Okay, I think I'm at the bottom of the slide, so I'm going to stop here. Thanks a lot for watching. Obviously, if you have any questions about this, you can ask them on the Ed forum, but I stop here. And I'll see you in the next video, I suppose, after the break. Okay, so thank you so much for listening, and see you soon.